The European Space Agency's Planck probe has taken the absolute best, finest resolution picture yet of the cosmic microwave background. NASA's Wilkinson Microwave Anisotropy Probe, better known as WMAP, is the one referenced in your textbook as providing all of the latest, greatest cosmological data. But the European Space Agency's Planck satellite has recently improved the picture. Nevertheless, the basic conclusions about the universe have not changed. Let's look again at the cosmic microwave background power spectrum. Again, this is a graph of the deviations from normal temperature as a function of the size on the sky of those deviations. And that very large peak you're seeing in the middle of the graph is telling you that lumps in the microwave background radiation of about 1 degree in size are by far the most common. Why did sound waves of that specific size leave a so much stronger impression than sound waves of other sizes? Sound waves of all sizes should have been percolating their way through the original plasma of the early universe, but only certain specific wavelengths are displacing the original plasma to a large enough degree that we're seeing their impression in the cosmic microwave background. To understand why, consider the passage of sound waves through a pipe when you blow at one end. There are certain specific wavelengths, or specific frequencies if you prefer to say it that way, of waves in the pipe that will lead to the strongest displacement of air at the opposite end of the pipe. At the top part of this picture, you see the longest wavelength sound wave that will produce the strong displacements. In that case, exactly 1/2 of a wavelength is fitting into the pipe. Now look one down in the picture. In that pipe, 1 full wavelength is fitting within the pipe. The next one down, 1.5 wavelengths fit in the pipe. And in the bottom part, 2 wavelengths are fitting in the pipe. In each case, the wavelengths differ by exactly 1/2 a wavelength fitting in the pipe. Now, waves of other lengths could also fit in the pipe, but they wouldn't produce the maximum displacement of air at the pipe's far end. The situation with the cosmic microwave background image is that the sound waves were percolating through the universe from a much earlier time, but what we see is an image of the universe at the time of so-called recombination, when hydrogen atoms formed from the original plasma of protons and electrons that were loose. It is the particular sound waves that had wavelengths that led to maximum displacement of the original primordial plasma that we are seeing, and those wavelengths will differ by exact half-integer multiples. That is why, in the power spectrum of the CMB, we see the strongest displacements at angular sizes of about 1 degree wide, 1/3 of a degree wide, 1/5 of a degree wide, and so on. Those displacements are called the acoustic peaks. The top of each peak is where we see a strong enhancement in the density of the cosmic microwave background. There are also valleys where we see the opposite, a region where the temperature and density that we perceive in the cosmic microwave background is less. Those occur with angular sizes of 1/2 a degree, 1/4 a degree, 1/6 of a degree, and so on. So if we're counting both up and down in the waves, we have features showing up with angular sizes of 1 degree, 1/2 a degree, 1/3 a degree, 1/4 of a degree. It's harmonics. It's basically sound wave harmonics, as if the universe stretched out through time was some sort of flute. Those sound waves reveal some significant details. For instance, while the first acoustic peak is very strong, the second acoustic peak is no stronger than the third. It turns out that if all of the gas in the universe was the only kind of matter present, we would have expected the second peak to be of a strength somewhere between the first and the third. Yet the second peak is suppressed. Why? The only explanation that fits is that the dark matter behaves differently from the ionized gas. Recall that these sound waves were first produced when matter began to clump together under the influence of gravity. It was mostly the dark matter leading the way in that clumping. But if the dark matter is what we think it is, weakly interacting particles, then the dark matter will pass right through ionized gas as if the ionized gas wasn't even there. So when the dark matter fell together into clumps, it just sat there in those clumps. But when the ionized gas followed the dark matter into the clumps, the ionized gas did what gas does. It rebounded back and made ripples of sound waves. That separation between the gaseous matter, made of the familiar atoms we know, and the strange weakly interacting dark matter led to a second peak that was weaker than what would have been the case if all of the matter in the universe was the more familiar stuff. Once again, we have evidence that dark matter is real and that it is weakly interacting. So studying the acoustic peaks has told us very important stuff. What else can we learn from the cosmic microwave background's power spectrum? Let's look at angular spans across the sky that are larger than the first acoustic peak. Those are relics from the inflation era, way back at the universe's extreme beginning. We see them today because of a phenomenon known as the Sachs-Wolf effect, which is that when a photon goes into a region of high gravity, it dips into the space-time distortion, and then, if the universe expands during the time it's making that dip, it comes out with a different redshift than what it would have shown otherwise. That we see these features on the cosmic microwave background shows that there were little differences in the density of the universe back at those much earlier times. There really was earlier structure back in the first instant of existence, and those were gravitational in nature. It wasn't sound waves produced by some object coming into the universe and shoving gas around. What originally shoveled the gas around was gravity from space-time distortions in the very early universe. Just one more feature worthy of note is that the higher frequency sound waves in the early universe became weaker and weaker the higher and higher frequency they were. This was called silk damping, and it's because the gas in the early universe was of an extremely low density compared to, say, the air that we move around in here today. Higher frequency sound waves require denser gas in order to travel. So this provides an independent check on what the density of gas was at the time the universe first became transparent. But enough of dry graphs. Let's regroup and look at the big picture. We've described a universe that began at a time of quantum fluctuations. There was then sudden and enormous inflation of space. All kinds of things happened in the next while until we get the image that we see today of the afterglow of the light from the Big Bang from 380,000 years after creation. When we look out in any direction, we see the image of that Big Bang afterglow all around us. More than 13.7 billion light years away in light travel distance, we see the universe as it was more than 13.7 billion years ago. After the universe first became transparent, there was a dark age, a time before the first stars. And then the first stars began to form about 200 million years ago, eventually developing into galaxies and the universe that we see today.